Hello everyone, this segment is going to be a demonstration of the ANSYS Simplorer software which you're going to be using for the next two computer lab assignments. Simplorer is a circuit simulator like SPICE, but it also is able to simulate other physical domains like hydraulic, magnetic, mechanical, and thermal. The example I've chosen to illustrate is from pages 95 to 100 of Gross's textbook. It's an elevator system with a counterweight driven by a DC motor. So in this example we're going to be able to illustrate electrical, rotational mechanical, and translational mechanical systems. So let me start a new project in Simplorer. When I do that, I get a component tree on the right hand side, and in the middle a blank schematic to start building my system model. A lot of times I'll call it a circuit model, but it's really a system model. So I'm going to start with the mechanical system, and this is going to be, we're going to pick the velocity force representation. It's more convenient that way because I'm using a motor in the system which rotates at a controllable speed. So let me put down the masses that represent the elevator and the counterweight. So I can click and drag a couple of masses onto the schematic, and I'm in multiple component placement mode until I hit escape. So let me place two of them, and I'm going to hit Control E a couple of times to zoom in so that you can see this. And I will double click on the left hand one, which is going to be my elevator. And its mass is, if you remember, it was 1,000 kilograms plus I'm adding half of the weight of the cables. The suspension cables that suspend the elevator and the counterweight from different parts, different sides of the drum. So it's 1,204 kilograms plus 75 kilograms per person, so it's 75 times NP. And this illustrates another nice feature of Simplorer. As soon as I type the NP, it's a name of a variable that's not defined yet, so I'm going to put in a nominal value of 10 persons. And I'll click OK, and that defines my elevator. And then on the other side is going to be my counterweight, which I'll call CW, and it's a constant mass of 1,429 kilograms. That includes the counterweight, which I believe was 1,225 kilograms, and then half the cables. So that's not entirely accurate because as the elevator moves up or down, you don't have exactly half of the cable weight on each side of the drum, so this is just an approximation. So that's the mass. It's got to be work against the force of gravity, and I will model that with a couple of force sources, which I'm going to add one for each mass I've defined, and I'll hit escape and stop there. So the one on the elevator side, I'm going to call that elevator grav, elev grav. And the amount of the force, I'm going to have that pointing down, so negative x direction is going to be downward in the shaft. It's minus 9.80665. That's the acceleration constant of gravity. And I want to multiply it by whatever the elevator mass is, because remember it's a variable. If I change the number of people in the elevator, that mass of the elevator changes, and if I say minus 9.8 times elevator.m, it's going to pick up whatever the mass value is and use that for the force due to gravity. And now on the counterweight CW grav, I'm going to put in the same negative g minus 9.80665 times the counterweight CW.m. So that's actually not going to vary because a counterweight has a constant mass, but rather than doing that calculation manually, this saves me a little bit of a manual work. Now I'm going to hook these up, and in Simplorer, if I float the cursor over one of those terminals, it changes to an X mark, and I click and drag, move to the right and click again. That connects the elevator with its gravity force, and I'm going to do the same thing on the counterweight side. And now I want to put a ground reference. This is on the toolbar to the upper right, and it has an electrical ground symbol on the toolbar, but when I drop it on the force source due to gravity for the elevator and the counterweight, it changes to Simplorer's version of a mechanical ground. So this is mostly my rotational mechanical system, and we have a drum that the motor's turning at the output of a gearbox. So I'm going to put in a rotational velocity inertia, which is the drum, and it's a constant inertia, so I'm not going to do any calculations. Let's type in the number. It's 199.7 kilogram meters squared. Sorry, that was the name. I made a mistake there. I want to call it the drum, and I want to put in the inertia of 199.7. There we go. So what happens if I try and connect this down to, say, my counterweight or my elevator? I'm going to draw a wire down to the counterweight, and it doesn't get placed. And look at the error in the lower left. A connection cannot be made between pins of different natures. So I can't connect, for example, an electrical pin directly to the mechanical pin. I need some kind of energy conversion mechanism. So we'll do that in a little bit. First, I want to complete the rotational side. Remember, there's a gearbox in there. So I go to the multi-physics mechanical system. It's under transmission and gearbox, and I want the ideal gearbox without any losses. So I'll place that on my schematic here and give it a little bit of room. And on the right-hand side, pin number 2 has the highest number of gears, so it's going to rotate the slowest. On the left is pin number 1. It's got the smallest number of gear teeth, so it's going to rotate the fastest. That's where my motor is going to be. So remember, the gear ratio is 40 to 1. So I'll call this gears, and the value is 40 for the rotational the gear ratio. And now that one I can connect directly to the drum. Great. But now I need to get this hooked up to the elevator and the counterweight. So that's done. It's going to be a coordinate transformation. The drum has a cable draped over the top, and one side hangs down on the elevator side, the other on the counterweight side. So if you remember the basic geometry, the ratio of the rotational speed to the linear speed on the tangent point on a drum is equal to 1 over the drum radius. So I'm going to put in a transformation, and I'm going to use 2 of them. The one I want is, let me slide over, we want rotational to translational. And I'm going to put 2 of them in because I have 2 sides of the drum. So I'll put one here and one here, and I'm going to rotate them. If I select one, the hotkey is Control R, and I'm going to do that 3 times for each one, so that I have the rotational part pointing up to where my rotating drum is, and the translational part at the bottom points down to the elevator and the counterweight. So on the one on the left, the one's going to be connected to the elevator. I'm going to call that the payout wheel, and my value K is the transformation ratio. It's the angular velocity over the linear velocity, and it's 1 over the radius. So remember, the radius is 40 centimeters or 0.4 meters, so it is going to be 2.5 is my transformation ratio. And I'm going to have a similar one on the counterweight side of the drum. I'll call this a take-up, and its transformation ratio is the same, except that I'm going to put in a negative sign, minus 2.5. So what that means is, as the drum rotates, the counterweight side is going to maybe decrease x, and the elevator side is going to increase x. So the elevator and the counterweight move in opposite directions. That's what my different signs for the K ratio implement there. So now I'm going to be able to wire these things together, like so. And I'm not getting any error messages when I do this. So my mechanical part of the system is all connected, and I'm going to hit Control S to save. It'll be Project 3. Great. So in order to drive the gearbox, we use a DC motor. And in Chapter 3, Gross just said, okay, here are the torque requirements and the speed requirements, and we didn't really put a specific motor in there. In this example, we're going to connect up an electrical motor and drive it with a voltage source. So in order to do that, these are under the basic circuit elements, electric machines, DC machine, and I want the one with the mechanical connection. I'll drop that onto the schematic and hit escape. So there's my pin, mechanical one, that represents the motor shaft, and I'm going to connect it to the gearbox. Now I'll double click on it, and where the data comes from is later in Gross's textbook in chapter 9. He takes up this example again and specifies a specific 75 horsepower motor to run this elevator system. And the data comes from table 9.4. So I'm basically, for this motor, reading some of these parameters right out of table 9.4. So the armature resistance is 0.2038 ohms. And we'll cover this in more detail later in the course when we talk about DC machines. My inductance is 0.011 henries, or 11 millihenries. The motor constant in Gross's textbook is called Ka phi, and its value is 2.626. That's what describes a conversion of current to torque. I have a moment of inertia of 0.828 kilogram meters squared, so that's going to get added to the drum inertia. And I have a friction coefficient, 0.02806 Newton meter seconds per radian. In Gross's textbook, that is called KRL for the running torque losses. So I haven't talked about the default outputs yet. At the bottom, for the motor, we see these check boxes. For example, TI is the internal torque. Paradoxically, it has units of amperes, so I have to remember that when it comes time to create the plots. But I can also get outputs of the current, the voltage, the speed, and that's going to be RPMs actually, and then omega is the rotational velocity in radians per second. So with a very large system, if you have everything saving all of its output, you can have very large output files, and so you may want to prune some of these from your model, but for this simple example, relatively simple, we don't need to worry about that. Okay, so we have the motor with a couple of empty pins that haven't been connected yet. I'm going to apply a voltage source to it, just one, and I'll double click and edit that, and I'm going to call it source. These mimic the types of sources that are available in SPICE. So I want a trapezoidal shape of magnitude of 532.5 volts, and that number was determined by trial and error. In a real elevator control system, you need some kind of control that and sensors that knows where the elevator is, how fast it's moving, and will adjust that voltage up and down to make the motor position the elevator precisely at the floor where people get on and get off. So I'm going to put in a rise time and a fall time and a pulse width, which is at the top of the triangular pulse, trapezoidal pulse of 1 second each. It'll be clearer later on when I'm able to show a plot of what that voltage waveform looks like. So let me connect then the source input to the motor, and I'm going to ground from the toolbar both the source and the motor. And in this case, it looks like an electrical ground. I'm going to save it, and let me set up the analysis to run. So when I click on the Simplorer project in the tree, you see that I have the number of people as a project variable. So if I wanted to change it from 10 to something else, like I could do that here. In order to run an analysis, the tree structure is similar to Maxwell finite element. The default analysis for Simplorer is a transient analysis, TR, just like in SPICE. Instead of 40 milliseconds, I want to run it for 3 seconds. I need to change my units from milliseconds to seconds. And Hmin and Hmax are the minimum and maximum allowed time steps. So I don't need to change them for this example. What it means is that Simplorer will probably start with a 10 microsecond time step, and as it realizes that things don't change that fast, it'll allow the time step to increase up to 1 millisecond. So at this point, I believe I am ready to run if I didn't make any mistakes. I'm going to center the schematic. should more or less parallel what you can see in the figure on page 95 of Gross's textbook. So I'll right click on the analysis task and I will click Analyze. And if all goes well, you should see a progress bar on the right hand side as it's simulating. That happens pretty fast. And if I can look at the errors and warning messages here on the lower left of the Simplorer window, I don't see anything other than normal progress messages, so it looks like everything ran properly. I want to look at some plots. So I'll right click on the results category, create standard report, a rectangular plot. And I want to make a number of these. I'm interested in the acceleration, so select both of them for the counterweight and the elevator. Make a new report. Let's see what else I want. Angular speed. It's interesting to look at the drum speed in omega and the motor speed. Those are on different sides of the gearbox. And I would like to look at the motor torque, except that it's a little odd that it's under the current category. It's got units of amperes. That's an internal torque. So I'll look at that. I want to look at the elevator and counterweight position. So that's under the length category because of its units. I'll make a report there, and then I wanted to show you what the voltage source wave shape looked like. So I only need one of those. I'll look at what's applied to the motor. Okay. So I've made looks like 5 different plots there. This is the wave shape of the voltage applied to the motor. So you can see it increases from 0 to 532 volts linearly over the first second. It holds a constant voltage for 1 second, and then linearly decreases to 0 in the third second of the simulation. Let me look at the second plot, well actually plot number 4, which is the position of the counterweight in the elevator. So my reference, my starting point is 0 meters, and you can see that the elevator is moving up approximately, almost 4 meters, maybe 3 and 3/4 meters, and the counterweight in red moves down. So they move in equal and opposite directions. That's what my plus 2.5 and my minus 2.5 transformation ratios in the payout and the take-up reel did. If I wanted to rename these plots, I can right-click on the plot name XY plot 4, click rename, and I can say that these are positions. And that'll update my title at the top of the plot. Let's look at plot number 3, which is a motor torque. And you can see that to accelerate the elevator moving up, it's got to supply a little over 300 amperes, it says here, but that's really Newton meters. And that occurs for 1 second, and then it's going to drop to about 60 Newton meters for the next second. That's to keep the elevator moving, and it's overcoming the force due to gravity on the people, but it's not accelerating. And then finally, when it comes time to slow down, the motor torque turns negative, and so it's recovering some of the energy. We have positive torque and negative torque, so we're recovering some part of the energy into the electrical system. Okay, let's look at the next plot, plot number 2. These are the speeds on different sides of the gearbox. So you look at the motor, which reaches 200 radians per second, and then you look at the drum, which rotates slower. The ratio between those is 40 to 1, and that shows the effect of the gearbox. And the last plot that I've made here, actually the first one in the creation sequence, is the accelerations. So if you remember from the narration of the example in the textbook, the target was the acceleration should only be 2 meters per second squared. And so we more or less meet that. The elevator acceleration, this is what the people in the elevator experience. It starts up with +2, and then when it's moving at a steady speed, it's at 0, and they're slowing down and it's at -2. You see that there's some overshoot. This is caused by the inertia in the system, and there's some damping, and the only damping in there is due to the motor running losses, that KRL function that I put in there. So we do momentarily reach a peak of 2.6 meters per second squared, and then it settles out. So things that Simplorer can be used for is maybe to try and minimize that overshoot, to design a control system that it's going to more precisely control where the elevator ends up at a certain period of time. So you would implement a sensor, attach that to the schematic, and maybe feed that back into the control voltage source input. I'm going to put a finished version of this on CourseWeb with all the plots named, and so that you can look at that at your convenience. But for now, this is just a basic introduction to Simplorer for you to use during the next 2 lab assignments.